Hello, my name is Elizabeth Butler, and I'm doing my report on the Fourier-Mellin transform and its applications to pattern recognition. So my abstract is the Fourier-Mellin transformation is widely regarded in digital signal processing as well as image processing. This transform enables rotation, scale, and translation of an image, which gives the Fourier-Mellin transform, or FMT, an advantage over other algorithms. I plan on using this algorithm to detect an image, although it may be rotated or on a different scale. This experiment will be done primarily using MATLAB. My plan includes finding a suitable image to transform, or taking an image or images, finding a general pattern recognition algorithm to compare to the FMT code the algorithm in MATLAB, run tests using the images previously selected, and finally analyze the results. The Fourier-Mellin transform is an integral transform developed in the late 1970s for pattern recognition. It is also used in digital signal and image processing and is very closely related to the Laplace transform as well as the Fourier transform. The Fourier-Mellin transform enables rotation, scale, and translation of an image. This can be useful because other pattern recognition algorithms have a difficult time with these variables. This algorithm will be tested for its effectiveness regarding rotation, scale, and translation. These tests will be conducted in MATLAB. The FMT is based on a combination of both the Fourier transform and the Mellin transform. The Fourier transform is one of the most important, if not the most important, transformation in signal processing. It decomposes the function of time, also known as a signal, into the frequencies that make it up. What this means is that it will transform a frequency in a time or spatial domain into a function in a frequency domain. The Fourier transform shows that nearly any function can be broken up into a sum of sinusoidal functions, characterized by amplitude and frequency. This can be demonstrated in the figure shown below, where a step function, which is generally what an edge in an image is represented by, can be reproduced by summing many different sine waves. The Fourier transform and the inverse Fourier transform can be shown in the following equations shown here. Fourier transforms have long been used in pattern recognition to find patterns or shape in complex scenes. Typical examples include recognizing faces in a crowd or finding a military target in a complex environment with other similar but non-military vehicles. The technique involves performing a correlation function between a reference image containing the pattern to be recognized and a test image that may contain a copy of the reference image. While the correlation function can be calculated directly, it involves a large number of multiplications and additions, especially on large images. When images are large, it is faster to form the fast Fourier transform of each image, multiply the Fourier transform of one image with the complex conjugate of the second, and then inverse Fourier transform the product. This forms the correlation of the two images. If one image is the reference image that you are looking for and the other image, that is considered the matched filter for the reference. The correlation image is the two-dimensional image that represents the correlation of the images at different shift positions, indicating the location of the object. That is, if a reference face is in a picture of a crowd, the correlation will form a peak at the shift position associated with the location of the face in the crowd. Thus, the location of the face is indicated along with the likelihood of that being the reference face. This would have obvious application with finding a particular person walking into an airport or checkpoint. You can see in the images shown here that there are two of the reference images in the crowd of the test image. The FFTs are also shown, and the correlation is shown that provides the existence and location of the reference image in the test image. These two correlation peaks indicate the likelihood of finding the correct pattern and the location of the pattern in the test image. This could alert an operator to the existence of a particular person in a crowd and their location. The method of finding patterns in a large scene using FFT-based match filtering is very powerful. The Fourier transform is said to be shift invariant since the object can be anywhere in the scene, shifted in X or Y, and the magnitude of the FFT remains the same and remains centered at the origin of the frequency domain. This match filtering or correlation method will work when the sought pattern is located anywhere in the image, invariant of shift. However, this method is not scale or rotation invariant. That is, if the object is a different size or rotated in the test image, the correlator may not find the object. For example, the arrow shown here has a very high correlation when the reference and test image have the same scale and rotation. The scale and rotation problem in matched filtering can be controlled in some environments. A camera mounted on the ceiling of a hallway in an airport, pointed down at a fixed angle, will generally see faces at a fixed distance and thus scale. Most people hold their head upright, so rotation may be acceptable for correlation. In other cases, scale and rotation cannot be controlled. If the filter thresholds are lowered enough to take significant scale and rotation into account, the filter will also allow many false targets to pass, therefore giving false alarms. Since a Fourier transform is shift invariant, there must be an image transformation that would create other invariances such as scale and rotation. One such transformation is to convert the Cartesian coordinates to polar, r theta. In this fashion, rotation in Cartesian domain becomes a linear shift in the polar domain. Another transformation is take the logarithm of r to form log r, so again scale changes in Cartesian domain become linear shifts in log r theta domain. We'll call this new domain log polar. This domain converts rotations into linear shifts along the theta axis and scale changes in shifts in the log r axis. Note in the image shown here that the mapping from the Cartesian to log r theta creates a very unusual distortion in the image. Because the image is transformed so non-linearly, it creates some sampling issues that create noise in downstream steps. Some of this can be helped by using better interpolation, cosine, cubic, least squares, etc., but I used a linear fit here. Note in the log r theta image above, the black shape at the bottom is the number 0 at the origin of the Cartesian image. The numbers 1, 2, 3, and 4 are linearly spaced across the middle, showing the conversion of rotation in Cartesian to linear shift in log r theta. The numbers at the top 5 through 16 get smaller as log r. Rotation in Cartesian domain creates a shift left and right along the theta axis. Also, a scale change in the Cartesian domain will cause a linear shift up and down the log r axis. Now that scale and rotation have been converted to linear shifts, the Fourier transform can be applied to determine if the reference pattern existed in the original image. Next, we will use the log r theta transform and see if it looks better with regards to scale and rotation. You can see here that the test image is 50% the size of the reference image. In the correlation, it can be seen that the white dot is moved up about halfway, which is about 50%, showing that this is in fact 50% of the reference image. It isn't moved over left and right because it's still at 0 degrees rotation. In this slide, you can see that the test image is rotated 120 degrees, but still the same 100% scale. These images shown show the sequence of events to form the log r theta correlation, otherwise known as the Mellin-Fourier transform. The reference image is Fourier transformed, log polar transformed, and Fourier transformed again. The same sequence is applied to the test image. These two Fourier transformed are multiplied, and the product is inverse Fourier transformed to create the correlation. In the example shown in the previous slide, the correlation shows that a significant correlation occurred at 0 theta and 50% scale. Now that it has been determined that the reference exists in the original scene, the face in the crowd, the reference can be scaled and rotated to match the Mellin-Fourier transform's result, and the location of the reference in the original image can be determined by correlating the scaled and rotated reference with the original test image. That is, multiple applications of Fourier and Mellin-Fourier transforms can take advantage of the shift, scale, and rotation invariances to detect the presence and location of an object in a noisy scene or face in a crowd. So you can see here there's a crowd of people in this test image, and there happen to be, I think, 4 of the matching faces here to compare to the reference image. Note that the correlation in the log r theta domain does not correspond to the location of the reference images in the crowd. Rather, the correlations correspond to the scale and rotation values. In this case, there were 2 cases of a 25% reference, one at 50%, one at 100%, and one at 100% but rotated 30 degrees. These values would be used to create new reference images and perform a correlation on the original image to determine the location. This slide shows a close-up of the previous image that shows the results of the transform. As you can see the 25% scale with 0 degrees rotation, 50% scale at 0 degrees rotation, 100% scale with 0 degrees rotation, as well as the 100% scale with 30 degrees rotation. The Fourier transform is a useful tool in finding targets or objects in complex scenes or noisy environments via matched filtering. However, matched filtering requires some knowledge of the scale and rotation and is not robust when these vary. By contrast, the Mellin Fourier transform uses the log polar transformation to convert scale and rotation into shift, to which the Fourier transform is invariant. The Mellin Fourier transform can detect and ultimately locate reference images in a complex scene over a wide range of scales and rotations. The log polar transformation almost certainly creates aliasing, since the effective sampling is very nonlinear. While I used a linear interpolation, a higher order interpolation in the transformation could have helped. I did not create the new references based on the scale and rotation information, but this step is not computationally difficult and could be implemented in face recognition systems. So in conclusion, scale and rotation invariance was demonstrated using a MATLAB rendition of the Mellin Fourier transform. This transform could be used for finding faces in a crowd, finding people in security cameras in crowded places, for example. It also has many other uses, such as military to find targets in complex scenes, as well as medical to find cancer cells and tissue samples. And you can see my references on this next slide. That is my presentation. Thank you very much.